All right. So our project on solar panels, we're going to talk a little bit about the application of physics behind those things, and we actually start with looking at the atomic structure of a solar cell. So as you can see here, this is what a typical solar cell would be. The main component of it is silicon. The reason why is that's the best semiconductor that we currently have. And basically, why we want a semiconductor is because we want to make sure that once the energy comes in from the photons, we could use that and direct it through our wire to collect the energy from the sun. And as you see here, we actually dope um, the material on this upper sphere. We dope it with phosphorus, and the lower sphere it's boron. And the reason why is because silicon naturally has 4 electrons, so it's actually going to use all of those to bond. And in order to really have collect the energy, we have to make sure that it's easy to break off and create bonds. So phosphorus has 1 extra electron, and boron has 1 less electron. So that way they will always move down and create this polarization, and that creates the potential difference. So once the photon hits, that will create that will kind of just move the electrons through this wire and to a energy source. All right, and then the solar panel module, like this would be, this would have many of those solar cells we are just talking about, and as a lot of interesting components. First, obviously, we just need glass just to protect it from any outside material that might be there, like rocks or just anything really. And then anti-reflective coatings next. If you notice, it's a blue color because we want something that absorbs light, but like not something that absorbs it completely. So blue is a very nice balance of that. And the reason it's anti-reflectory is because we want the sunlight to come in and reach the silicon. So what this coating has actually is it reflects the photons on both sides of it. So once it comes in, it just bounces off twice and just keeps going down. And then the metal grid, the reason it's a grid and not like the metal plate is because yes, we need an outlet for the energy to like flow through, but at the same time we still need the exposure for the light to come in the first place and reach the silicon plate, which is the main component of this whole module. And typically 60 solar cells would result in 300 watts under direct sunlight, and 4 hours of peak sunlight can be expected in a typical day. And the purpose of our lab really is just to understand how solar panels work, find out their max efficiency using testing different variables, and just, I guess, grasping a real world application of how it relates to our everyday lives. So the first thing we decided to do is to actually calculate the power output of the sun. And the way we did that is we just used one of our little solar panels that we bought. We just use a multimeter to find the current and voltage of that solar panel for, I guess, a given time. And then what we actually did is we just worked backwards with efficiency to see just how much watts, I guess, came in before like the got used up. So for example, for air, we found out that solar panels are generally around 15 to 20% efficient. Our solar panels are not commercial, so we just went with the 15% efficiency mark. And working backwards, we found out that before it hits the solar panel, there should be about 2.8 watts in the air. And then, according to NASA, 23% of incoming solar energy is absorbed by the atmosphere. So we did the same process and we got 3.64 watts. As you can see here, that's the distance of the sun to the Earth. So that what the next, I guess, part would entail is to create a sphere around the Earth to see just how much total energy that the sun is, I guess, exposing us to. If yeah, and then well, all we do really is just we find the area of both components, and we just kind of create a proportion to see, okay, if this area of the solar panel got us 3.64 watts, how much would the whole output of the sun give us? And we got 1.65 times 10 to the 26 watts, and that is relatively close to what Wikipedia told us it should be. So just putting it on the context, this calculation also shows that to, I guess, match the power output of the sun, we need 3.846 times 10 to the 17 nuclear plants, which is like crazy. And if we actually take the power output of the sun and I guess just use it absorb it in 1 year, it would last us for 8.36 times 10 to the 14 years. But obviously that is outside of our reach. It's just very interesting to see in perspective. Now we're going to actually analyze the construction of the solar panel. And I think this is Malav.
Yeah. So earlier we mentioned that silicon is a semiconductor, but we don't really know what that means. So a semiconductor can act both as a conductor and as an insulator. The way it works is it needs to reach a certain, let's say, activation voltage. So if a voltage hits the semiconductor, it activates and acts like a conductor. So to test this, the first thing we did was we covered up the solar panel completely so no lights got through. And if you look at the first picture, it's hard to see, but it's on the voltage scale and it says the voltage is 0. So if the voltage is 0, that means the semiconductor was not activated, and right now it's acting like an insulator. So we measured the resistance, and that's on the bottom picture is on the resistance scale, and it's at 20 million ohms right now. So we read resistance of 2.76 million ohms. That is very, very high. That means this is acting like an insulator. We also did this again outside where we did have a voltage and the resistance was very, very small. That means it was acting like a conductor. So we know this solar panel is made out of a semiconductor. Can go to the next slide. So then we wanted to know how solar cells are assembled. Well, this whole thing is a solar panel, and it's made out of a bunch of different solar cells. So the way you can assemble solar cells is you can either put them in series or you can put them in parallel, like the diagrams I have drawn. So when you put them in series, you tend to increase the total voltage of the panel. And if you put them in parallel, you tend to increase the general current. So how do we figure out how they're assembled? Well, we did an experiment where we covered the panel in different ways. If you go to the next slide. So the first thing we did was we covered the solar cells perpendicularly. So if you see the lines, we covered it so our paper was perpendicular to those lines. That will cover the cells perpendicular. Go to the next slide. We measured the voltage, and we graphed it versus the area covered. So as you can see, the general trend here is the voltage remains the same for most of the time until it's almost completely covered. And then it starts to drop. As you can see, there's a little bit of error in this. It doesn't completely drop to 0. This is probably because we have some light leakage when we covered it. So there was probably some light seeping through and we were getting some voltage. If you go to the next slide. We did the same thing, but with current. The general trend here is it drops very fast and it goes to 0 completely. Go to the next slide. Next thing we did was we covered the cells in parallel. If the paper is parallel to the lines. Can you go to the next slide? The general trend here is the opposite of covering it perpendicularly. Here, the voltage drops as we increase the percent we cover. Once again, oh wait, all right, yeah.
I can't go back.
It's fine. All right. So here, the current stays relatively the same, and then eventually it drops to 0 when we cover it completely and no light is going through.
Actually, I could
go to the next.
Right here. Do you need it?
It's fine. It's fine. So what does this prove? Well, since both results gave us different both ways gave us different results, we know that our cells can't be assembled in one way. They have to be assembled in series and in parallel. So when they were covered perpendicularly, the voltage stays the same. So this shows us that the cells in the column, they were connected in series. But when we covered them in parallel, the voltage dropped, but the current stayed around the same. So that means the columns were connected in parallel. Next slide.